Hey, welcome to The Explainer. Today, we're going to pull back the curtain on this incredible magic trick your computer pulls off every single second. It's called concurrency.
I mean, really think about it for a second. Right now, you've probably got a browser open with who knows how many tabs, maybe some music playing, a file downloading in the background, and your operating system is secretly running countless other services. So how in the world does it manage this invisible dance without just, dropping everything? All right, to really get this, we're not going to start with a bunch of confusing code. No. Instead, I want you to imagine the busiest, most chaotic restaurant kitchen you can picture. Because, as you're about to see, managing a computer is actually a whole lot like trying to run a crazy kitchen. Any kitchen, any great kitchen, is all about its staff, right? So let's meet the key players in our little computer kitchen. In our world, they're called processes and threads.
Okay, so think of a process like a head chef. They're totally independent, they've got their own private cooking station, their own personal set of ingredients, their memory, and their own recipe to follow. They don't share a thing. Now a thread, that's the chef's assistant. They work at the same station, using the same ingredients, all to help that one chef get their job done faster. They're lightweight, they're collaborative, and here's the key. They share that memory space.
And you know what's cool? We can actually prove this difference with a tiny bit of code. Let's imagine we give two threads and then two totally separate processes the exact same job. Just report back with your unique process ID or PID. Think of a PID as like the ID number on their employee badge.
So what happens when we run this? Well, the result shows you everything. You'd see that the two threads report back with the exact same PID. They've got the same employee badge because they're on the same team working for the same chef. But the two processes, they each get their own totally unique PID. They're two different chefs with two different badges working on completely different things.
Okay, so now we've got all these chefs and assistants running around the kitchen. It's getting crowded. Who's in charge here? Who's telling them what to do and when to do it? Who directs all this chaos?
Well, that's where the scheduler comes in. This is the ultimate head chef, okay? The one standing right in the middle of all the chaos, calling out the orders. Its entire job is to decide which task gets to use the most important resource, the CPU or the main stove, at any given moment, making sure everybody gets a fair shot.
And one of the simplest, fairest ways this head chef runs the kitchen is with a technique called round robin. It's super simple, really. Everybody gets a small, fixed amount of time on the stove. We call it a time slice. So task A gets its turn, then task B, then task C. And if a task, like A, isn't done yet, no problem. It just gets back in line and waits for its next turn. See? No one gets to hog the stove.
All right, things are looking pretty good. Our kitchen's running, the director's fair, but what happens when things get a little complicated? What happens when two assistants need the exact same thing at the exact same time? Like, say, the one and only spice rack.
This, my friends, leads to a classic, super common problem called a race condition. Let's imagine we have two assistants, two threads, and we give them a really simple job. All they have to do is add 1 to a shared counter, and they each have to do it 100,000 times. They are literally racing each other to update the very same number.
Now, the logic here seems totally straightforward, right? You start at 0, you add 100,000, then you add another 100,000. The final answer has to be 200,000. I mean, what else could it possibly be?
Yeah, no. The final number is something totally different, and it might even be a different wrong number every time you run it. So why? What's happening is they're stepping on each other's toes. One assistant reads the number, but before they can add to it and put it back, the other assistant reads the same old number. They're overwriting each other's work, and thousands of updates just vanish. Total chaos at the spice rack.
So how do we fix this mess? Well, the solution is actually pretty simple. We just introduce a rule. In programming, we call this a lock. It's basically like putting a little sign on the spice rack that says, "in use." When one assistant grabs the lock, nobody else could even touch that counter until the first one is finished and takes the sign off. And boom, just like that, with our lock in place, we get the right answer, 200,000. Exactly. It just goes to show you, this one simple rule, this idea of synchronization, is all it takes to turn chaos back into order.
Okay, so our kitchen is getting pretty sophisticated. We've got staff, a director, we even have rules for sharing. But what happens when the rules themselves backfire and bring the entire kitchen to a grinding halt?
Imagine our first assistant, let's call him Task 1, needs salt and pepper for a recipe. So they walk over,
They grab the salt shaker, we'll call that lock 1, and they hold on to it while they reach for the pepper, which is lock 2. But here's the kicker. At the exact same millisecond, another assistant, task 2, does the opposite. They go and grab the pepper, that's lock 2, and now they're standing there waiting for the salt, which is lock 1. You see where this is going, right? And now they're both stuck, just frozen. Neither one can move forward because each one is waiting for the thing the other one is holding. This is a deadlock. It's the ultimate digital traffic jam, and the whole kitchen just stops.
And look, this isn't just some random bad luck. For a deadlock to happen, you need these 4 things to be true all at once. First, only one person can use a thing at a time. Second, you have to be holding on to one thing while you're waiting for another. Third, you can't just snatch a resource away from someone. And fourth, the big one, you have that closed circle of waiting we just saw.
So how on earth do you prevent this from ever happening? Well, the easiest way is to just break one of those 4 conditions. And the most common one to break is that circular wait. We just make a new kitchen-wide rule. No matter what recipe you're making, you always grab the salt before you grab the pepper. By enforcing a strict order like that, that circular I'm waiting for you, you're waiting for me situation can never happen.
So there you have it. From the chefs and their assistants to the head chef calling the shots, all the way to race conditions and deadlocks, you now get the core rules of that invisible dance happening inside your computer every moment of every day. So now I'll leave you with this. Now that you know the secret rules of the game, what kind of amazing things could you build?